Kia ora. For those who don't know me, I'm Luke Veltman, and this year for my final year project, I conducted a comparative study between roller versus track fill compaction in New Zealand forests. Now, the situation, for those who have spent a bit of time working or involved in the New Zealand forest industry, you would have likely heard or worked with the term track rolling. It is currently one of the more common and widespread compaction methods for fill material in New Zealand forests. Now, why is this? To start off with, there is a simple lack of knowledge into the subject, making the effectiveness of track rolling unknown. This has led to this being quite a controversial topic between engineers, forest managers, earthworks contractors. They all take varying opinions on the matter. The primary attractiveness of track rolling is the fact that the machinery is already on site from carrying out the rest of the earthworks, thus saving money from not having to have another piece of machinery on site. It is also preferred in some cases where there are safety concerns around using a pad foot or a smooth drum roller on soft, uneven or undulating terrain. The objective of the study is to shed light on the difference in compaction between purpose-built rollers and track rolling when given the same site and soil conditions, as well as determining the optimum number of passes. The results of the study aim to enhance the industry's understanding of the effectiveness of the two compaction methods, along with other operational aspects for executing compaction. Across the study, testing was conducted on 3 sites, overall identifying 4 different soils. As you can see, these sites were scattered across the sort of central North Island area. Over the study, there were numerous steps involved for data collection and processing. These included scalar penetrometer testing, surface samples, dry sieving, standard proctor testing, along with other various steps for actually setting up the fill layer. These processes allowed for a variety of data to be gathered on the site conditions at the time of compaction, as well as compaction data. I don't really have enough time to explain in detail the processes which took place, but I'm happy to answer any questions afterwards. To give you a bit of an idea of how the fill layers were made up and tested, here's some pictures. The layers were made up in 750mm lifts, and as you can see, the length and width of the layers were made up to enable both compaction methods to be carried out on the same layer. This was purely to avoid differences in the soil conditions, which would overall create bias within the results. Site 1 was located in the Manawatu region outside of Hunterville, with testing being carried out on broken up papa material. At this site, both a D6 and a 7-ton smooth drum roller were used for testing. Data show that the smooth drum roller outperformed both at the surface level and at depth, with surface samples showing around 7% better level of compaction. Scalar results showed that track rolling had an optimum number of around 4 complete passes, where smooth drum was around 6. And by complete passes, I mean complete forward and backwards over. These results show that the smooth drum overall delivered significantly higher results, with between 25 to 45% greater compaction when comparing it at different depths of the profile. Site 2 was located in the Bay of Plenty between Rotorua and Tauranga. Both dry sieving tests and S-maps data determined that it was an elephanic clay soil. Compaction testing at these sites used a 14-ton digger and a 11-ton roller. The data showed that both track rolling and smooth drum rolling yielded comparable results, with dry densities of both lots of surface samples measuring around 8.3 kilonewtons per metre cubed. This correlates to around 94% level of compaction when comparing against that compaction curve. As you can see, the samples taken from the site show quite a high moisture content, above that of optimal. Because of this, the vibe was opted not to be used on the roller, as after the first pass, you could really see the ground was kind of turned to mush. It can be seen that for both compaction methods, the optimal number of passes was around that 6 to 8 mark. Overall, the soil showed poor strength when compared to the other sites. This is thought to be because of the high moisture content and the fact that it is an allophanic soil. The second soil tested at site 2 was a broken up rhyolite soil, which had a composition which fell into the sandy clay loam category. Given the on-site compaction conditions and the compaction curve, surface samples showed that the track rolling achieved 94.8% level of compaction, whereas smooth drum achieved 98.7%. It shows that track rolling has optimal around 4 passes, whereas smooth drum was around 6. When comparing the results, track rolling achieved on average 26.6% poorer than the smooth drum roller. And then when you actually look at it with depth, it can range anywhere between 35 and up over 100% greater when using smooth drum. Site 3 was the final site located off the Napier Taupo Road and had a sandy loam soil. The compaction curve for this site showed that the optimal moisture content was around 15% with a maximum dry density of around 15.9 kilonewtons per meter cube. The machinery used at the site was a 11-ton pad foot roller and a 22-ton excavator. At the site, it showed that pad foot rolling achieved around 14 kilonewtons per meter cubed at the surface level, whereas track rolling was around that 12.2 mark. With both compaction methods achieving having an optimal number of passes of around 6. When comparing the average strength of the layers tested for either compaction methods, it actually showed little difference between the two methods when you took into account the number of passes and the depth. This could be attributed to the moisture content, which was higher than optimal. Now, this leads on to the conclusions or implications. Across all the sites, it was identified that with a higher moisture content than optimal, there could be seen minimal differences between track rolling and purpose-built rollers. This shows the importance of carrying out compaction under the correct site conditions, which match the material which you are compacting. For our optimal number of passes across the sites, it ranged between 4 to 8, but predominantly being around that 6th pass mark. In terms of costs, some wider implications of the study show that at the correct site conditions, purpose-built rollers could save money when carrying out full compaction for road construction, as they achieve a better CBR value, which in return means you don't need as thick a pavement. And this can range from the study and the sites. If you were going to build a road, it could range between 35 to 90 millimeters less pavement thickness. And safety concerns. Despite purpose-built rollers achieving better compaction for some of the locations tested, it is recommended that in situations where operator health and safety is of concern, such as using these purpose-built rollers on sort of that rough or unstable terrain, then it is advised to use a track bit of machinery. During the study, the lift thickness for the testing was 750 mils. It should be noted that this thickness is quite large. It was purely conducted in this way, so you could see that sort of change with depth. And it was quite clear that at those deeper levels, there was quite a reduction in the compaction achieved.